Okay. Yeah, thanks everyone. Let's start the talk. So basically, so what I'll do actually, I'll just go over the semiconductor trend, how things are changing with time, and how the market demand is also changing with the time, and how the whole technology industry is coping up with this change and increasing demand. So as you all know, right? I mean, the semiconductor is the backbone of for the industry for many generations and for its technological progress. So right from the basically IoTs, PCs, tablets, and smartphone, semiconductor changed the world. So it helps the consumers to stay more connected, and also the global connectivity today, it's playing a huge important role, and and it is growing exponentially, and that's the fundamental driving force of the technology or technological change, which in terms is demanding huge increase in semiconductor trend. So basically if you'll see so now however however there is a fundamental limit actually, so everybody knows actually that this growth trajectory has its natural limit. On top of it, in combinations of the huge demand, that that requires really transformation of this industry from where it was now, it was and now it is, and how it will be in future. So the transformation is actually is in the, is a ongoing process, and which pace it is transforming, it depends on the time frame where we are. So now if I go right, so if you can see, so I'll go a little bit on this one. So if you see from till, if I say, if I go back 5 6 7 years back, the demand was mostly because of traditional approaches, traditional demand. So and now the demand is because of the application which is data space centric, data specific. I'll come close, cover more on that. And the major see it is that this field is very diversified field. I mean, it has, if you see from the spec till that product, yes, it has so many steps, and so many diversified skill set you required to get into the final product. But instead, but this diversified field, the 70% of the capital expenditure, it comes from the top 5 players in the market. So because this is so diversified, so capital extensive intensive domain, not everybody can afford to be in this domain for a long time if the industry doesn't have their own sufficient capitals. So with that, I'll go I'll start with this slide. So in 1947, if anybody asks, right, what is the biggest innovation, greatest innovations in 20th century, so people may say car, right, or aeroplane, because of its mobility advantage to moving here and there. But what was important was the transistors. In 1947, the first transistors was invented in Bell Lab, and then from 1947 to around 1958, these transistors are used in IC. So, and these two inventions got Nobel Prize. That has that obvious reason for having that. And in the era of 1997, and this particular ICs scaled up. It means the number of transistor put in a particular die increased a lot. So so that's why the industrial application of the semiconductor also evolved. So initially it was like just a radio, and then TV, and then when large scale integration started during 1970s to 2010, all applications, all the computer applications basically are using the semiconductor chips, right? Yeah, if there is no talk to be completed if we don't mention Gordon Moore's name. So what it, and everybody knows it. I just touch upon it because it is important to touch. So what it says in 1970s when the large scale integration started, right? So basically, uh, that time here's a co-founder in Intel, and that time the expectation also growing because technology was also evolving and they are able to really innovate a lot of things in this domain, and that's why he set up an expectations, and that expectation is not just hypothetical, it was actually the real expectation to make sure that semiconductor will be relevant, this domain will be relevant only if we can double the density of the transistor in every approximately in every 2 years time frame. So what it means, if you have uh, today if you have x computational capacity of a device of of some price, after 2 years you should get a device of same price with twice computational capacity, so then only it will stay relevant. So that's what the expectation he said, and that show out quite I mean that was typically followed, means every uh, professional in this domain at least try to follow this, otherwise they thought that they will not be relevant, they'll be out of the market. And now you'll see how the things are changing. Now this is a very interesting slide actually. I mean by the way, by all my slides contents are actually I taken from internet, YouTube's and all, because this is not my domain, this is just for my interest. I do as introduced, right? I am a hardcore circuit design professional management side. So basically, so but I have my own interest through that I to analysis the domain and how the industry trend. So that's why I'm sharing it. So this is the slide from Applied Materials, one of the. So what it says that till 2018, the most of the data was generated by human applications through human through manual. The data was generated and the data generation was analyzed based on the that manual data generation. It means human has some degree of capacity, the amount of data it can generate, and it goes organically. But from 2018 onwards, when that IoT, machine learning and artificial intelligence came into the play, the data generation is taken over by machine instead of human. This means we are now generating ample amounts of data by using sensor, by using smartphone, by some other means. But what will do with the data? I mean, you have to store the data and you have to analyze the data and you have to make sense out of those this much data. So what it means that the application of the and how we can analyze the data, you have to have algorithm to analyze the data. So you have to have hardware capacity to analyze so much of data. You have to have hardware to store so much of data, and we have to have analytical capacity to make a pattern out of the data. So that's what it says. You can see, if you see 1.6 gigabyte of data, if I assume it was used for analysis in 2018, now 2025 it will be 157 zettabyte of data. So you see it's exponential growth of this industry. So it means we have huge going forward. You'll see it's like a while now. Everywhere, every part of your application will have semiconductor application. So only thing is that you have to stay relevant. You have to basically work on the things which will make sense in application specific. Am I hearing well, guys?
Yes, Bijan, yes, please carry on.
Okay. So this is another slide from Applied Materials. So this, it says that, see, you can see how each and every application is changing. Say for example, if you take a scale of 100 in case of smartphone 2015 to basically just let me see if I can. I think oh, let me how can move it. And yeah, okay. So you can see the smartphone applications will grow about 62%, and then basically the auto industry, electric vehicles industry, which is the current trend now. We can see every say China, America, even India starting to cope up with this EV domain. EV domain. Okay, everybody is working on EV domain, so that's required uh, ample amount of ICs, semiconductor ICs. And then data centers actually is PC, your CPUs, uh, a cloud everywhere in it, that growing ICs. So you'll see 99% increase in semiconductor contents in data centers. And then hopefully applications, all the smart homes nowadays, if you see all the IoT applications, smart homes also use the semiconductor content, and they see is doubling, almost more than doubling, double actually, the rate it is growing. So as I said, the driving force mainly basically in these industries are industry 4.0 and smart factories. Smart factories means factory also be automated now. Otherwise, they will not be able to make the kind of production they want without this space, right? And so they have to adapt the automations. And automation adoption means it requires software and hardware. That is where again semiconductor comes into place. And then optimization of the supply chain, manufacturing, industrial IoTs, the other drivers. And then big data I already mentioned is artificial intelligence, machine learning. These are the two major applications. So I cannot cover in basically one or two lectures in artificial and machine learning how hardware is related to software and how both combined together. It's a very specific domain now, is going to going to grow. And then cloud computing, data warehousing, and then 5G acceleration for the replacement cycle of the smart devices. And then the automotive sector, as I mentioned, electric vehicle, and then advanced driver assistance, that self-driving systems is also everywhere required. And then the growth, basically when we are 5 years before, right, we are not able to imagine how things are going to grow. We are just incrementally working on a few things on the PPA improvement. So for example, we get a request for the specification, give us, you got a technology, now technology will give you 10%. So can you architect your say circuit or memory which will give you 15%? So and the industry was satisfied with that. It's okay because I'm getting a little 5% more from your architecture now. But now the things, the demand is huge. I mean, you have to really break through your innovations. So basically, and then remote workplace is new normal now after this pandemic. So, and these are the semiconductor capital cycle. So you'll see how things are huge change, the demand changed actually. If you see the logic, memory content, analog content, and foundry content, you can see the memory content really grown a lot, along with logic. And then analog will be a part of the SoC, whichever, but it's not growing as fast as the digital content because of this application, because all these digital applications actually data analysis required more digital circuitry and the mixed signal circuitry rather than pure analog, and that foundry also. So this is the chart which shows how US stock is grown over say 10 years down, 10 years time frame. So the purple color shows the S&P index, which is actually the standard index for the US stock market. And the orange one is that semiconductor index. This contains actually all the top semiconductor major companies index, which shows how rapidly it is outspacing the other domain in financially. You can see that. This chart shows that this I have taken from AMD slide, one of the AMD slides. So this shows how the whole total, how the whole product cycle of a semiconductor. So you can see here. So basically, here the architect or logic, I mean, at the high level architect, they think what we should do, and then basically this is the design phase. This is the design phase. They are actually they implement all the behavioral netlist to the circuit level, and that they do the design and design the chip, and then it will go to the manufacturing, so to the foundry it will manufacture, then it goes to package and assembly. So that will be done for in different in different uh, vendor, and then it will go for testing, and then all those chips package chips will go to testing, and after finishing the testing it will go the board assembly. Actually then you'll have a board where you'll assemble all those chips and check the applications, and then basically it will go to the it will ship to the customer end. So you can see right from here how many steps we have to go through, and every steps are important, and the very few player contribute multiple steps here, but majority of the things that companies are focused on either on the design side or fabrication side, and then test assembly sides. So it is impossible to do by only one company for the whole thing nowadays. Yeah, so this shows the business model in the semiconductor industry. So how many business models generally followed, as you can see, right? They have to impact and contribute to all these basically task. How, I mean, how they place themselves in the industry, in the business model, so that they will be impactful and they get their own market share to be benefited from the huge demand of the industry. So integrated device manufacturer. So what it means is that the company who design the chip, they own fabricate they fabricate their own chip. So there are quite a few companies earlier. Now close to 2 to 3 companies remain now. So Intel used to design their own chip and also fabricate their own chip. So Intel was there, and Samsung is there. The Samsung have their own fab, and then NXP Semiconductor also had their own fab. So these are the three major players, and I don't know the future of it, whether the Intel will still be manufacturing their own chip or they'll outsource their manufacturing. So but I see a trend that Intel is also trying to manufacture their uh, very high-end chip to from TSMC. So this is one business model, and then fabless business model. Fabless business models, they will only spend their money on R&D, design, and get the uh, best design out of their skill set, their resources, and then get it fabricated by fab separately. So those companies are, say for example, Nvidia, Qualcomm, AMD, Broadcom, MediaTek, High Silicon. These are the players where I'll show you the chart. I have the chart. So the advantage of them, actually, they don't spend capital on fabrication. So that's a huge capital intensive business. So instead, they just focus on the design, optimizing the design, and let it get fabricated by some other player. And then foundries, they just do their fabrication. So they take the design from, say, Nvidia, Qualcomm, Broadcom, AMD, and they fabricate, they manufacture it, the integrated circuit, and then without designing it. So the company examples are TSMC Global Foundry, and there's SMIC, and then semiconductor equipment manufacturers. This is another important domain, basically, that we generally don't focus too much on this because these are the very niche player. I mean, there are who see if when new technology comes, you need machineries to basically do the fabrication. Nothing is manual there, right? So those are very very high end machines actually. So who all are can make those machines actually? So there are companies like Applied Material, Lam Research, ASML, and you can see the I'll show the how their market capitalizations are. And also remember these things, this thing came over generation, their skill set. It takes 30-40 decades to get that skill set to be leader in these markets, unlike only doing software and outsourcing. These are totally different domain. So it's not that tomorrow I'll wake up and say, man, I'm going to work on the equipment supplying domain. So it's not going to happen like that. So and then there'd be EDA. We know that. So we have software skill set in India. So Synopsys, Cadence, they are very play very important role in the semiconductor industry because nothing is manual now. Even though we are designer, we are architect, we call architect ourselves, but we do our job through the EDA tool. So and and tools are getting so important with more complex design, more complex basically circuitry. So in this player actually we have Cadence, Synopsys, and there are some players also. I'll just cover that. And then ATE, automatic test equipment supplier. So they, as I say, that just before board board integration, so it has to be your design has to be tested actually in the chip. So there are companies like Taradian, Ad, advanced advanced test corporation, AME holdings, etc. And then outsource semiconductor assembly and test. So there are actually companies which just do assembly and test both together. So that will, like AAC Technologies, Amco Technologies, JC Tech Technologies, etc. So here is the semiconductor ecosystem, industry ecosystem. I just simplified it here. Say for example, the equipment supplier will supply the equipment. It will go to the foundry will, based on the equipment, they will define a technology, and that technology, that equipment will go to both foundries as well as the integrated device manufacturer. So who does the design and test both, design and manufacturing both, and then foundries. And for example, simple example is the fabless company will come up with the design, optimized design, and it will go to fab, and they will fabricate the design and send it for OSAT. So basically, and then basically with the test automatic test equipment will supply to OSAT, and they will test the design, and then it will finally go for the finished product. So as I said, right, so very few companies actually does basically design, manufacturing, packaging and testing. So I see Intel and Texas Instruments, these are the two companies basically contributing broadly to this four domain actually: design, manufacturing, packaging and testing. And most of the other players are actually fabless player are playing a role here. Yeah, these are some of the companies I thought that they're growing very fast in their domain, and actually capturing the market. So this is some of the trend what we are seeing: Intel versus AMD. Everybody knows, right, how Intel is or AMD is competing. So if you'll go back say 10 years down before, right, so existence of AMD was actually survival of AMD was actually a question mark. But Intel was actually fully dominated that time because they have their own design, and fab. But what AMD did, they also fab initially. Then they came out of the IMD model, IDM model, and then just focused on the design only, and they outsourced their fab from TSMC. And then what they did, actually, they actually optimized their designs, chip design, in such a way that they focus totally on the design, and then TSMC is totally focused on the manufacturing of the high tech technology. So both the combination, actually, it's really performing both uh, the chip performance, power, and the area wise. So you see how AMD is taking out the market out from Intel, and that's why I say that Intel probably now it is actually working in collaboration with TSMC to get their high cutting edge technology, because focusing on both and spending capitals on both is getting difficult for them to be on the market. So this is the slide which shows the how the EDA players are actually market capitalization of the EDA players are. So basically, I think 40% is Synopsys, 27% is Cadence, and then 14% will be Mentor Graphics. Yeah, this is the foundry business. So you can see here. So if you can see how country wise actually they're contributing to they're capturing the market in the foundry. So most of the things are in Asia basically. So you can see Taiwan, 63% of the fabric foundry business is captured by Taiwan. Then distant far by South Korea. This is mostly because of by TSMC, and then mostly the 18% because of Samsung, and then China is having few fabs, the older technology, and 13% is the rest of the world. There are a few fabs in US also, US and UK. Now, if you look at the percentage of the market capitalization, so basically per company, so TSMC is actually having the market capitalization of 55%, and then 17% by Samsung, UMC 7%, Global Foundry 7%, SMIC 4%, and 10% other. This is the equipment manufacturer that, as I mentioned, right, how they capture, how is their market capitalization. So ASML 19% is a very, very high-end equipment supplier, and then Applied Materials is 20%. Lam Research is 13%. Tokyo Electronics is actually a good contributor for Japan, 13%, and 6% from KLA Corporation. Now, if you see the whole ecosystem, how they are distributed across the globe, so you can see this is West and this is East. So if you see the software, that is EDA, and the design, when I say that say software, I'd say the software company which is basically owned by that particular country. Okay. So for example, the US, right? All these companies are US companies, say Cadence, Synopsys. So basically, and then design, right? All the design companies, right? Intel, Qualcomm, Broadcom, Nvidia, there. So they are design. So they have few foundries here, but equipment supply. So majority of the things you can see the design and high-end R&D are sitting in the west side. So that is US, UK, mostly US. Whereas you can say foundry is mostly in the east side. As I shown, right, South Korea and Taiwan, they are basically holding the majority of it. And then equipment supply we have in Japan, Tokyo Electronics, and I see the Middle Eastern one equipment supplier. So it means how basically the industry is distributed and across the globe. So the question mark comes where India stands actually. So frankly speaking, India is very far behind in owning those piece actually. So basically, it doesn't mean that we are in India, but it doesn't mean that we don't own. Basically, we own very few things in the semiconductor component. We work as a R&D resource there, right? We don't own much because we don't have IPs, so many IPs, patents in this semiconductor domain. So this is the Intel's chart I'm showing. So I'll just show totally how is their product distributed actually. So they are having PC centric client and computing group of chips. 54% actually is actually the PC centric market, and then they have 32% data center. They are working on IoTs, about 4% they have IoTs, and then mobile, this low power application 1%, and then non-volatile memory solution they have 7%, and then programmable solution they have 2%. So if you see the stock PE ratio is 9.7%, so this very lucrative price now actually. So their total market capitalization is $191 billion. uh, Revenue growth average in 3 years is 6%, and operating margin is 30%. So if you see all of the semiconductor companies, right, in all sectors, all portion of the semiconductor companies, the gross margin, operating margin is quite high. And then capital expenditures to sell, if you see, it's 22%. So this is quite high actually. So it means to make profit they have to spend a lot of money to capital to make that profit. So, and the return on investment is 29.5%. Now where in contrast, if you go to fabless company like Nvidia, they are also work on CPU, but they are going to graphics processing unit. So if you see their business model, so stock multiple, you know everybody, right, how Nvidia stocks is doing. It's 85x, and then market capitalization is 324 billion. Revenue growth is 18% in average 3 years compared to what we saw. Intel was actually 6%, is 18%, and operating margin is 26%. One interesting thing here is that capital expenditure to the sale is just 4.5%, in compared to Intel it was 22.5%. So it is very less expenditure because of your fabless in nature, and the return on investment is 27.9%. And if you see their product diversification, so 43% of that revenue comes from the gaming, and 45% come from the data center. The mostly gaming and data center markets is captured by Nvidia, and then visual professional visualization 5%. Automotive, actually they are working on automotive, we also 3%, and then others 4%. So they do work on the crypto related chips also. The Qualcomm. So Qualcomm is actually there in mostly their focus is on the low power mobile centric business. So 78% comes from QCT, that CDMA technologies, and then 22% is licensing. So basically, then if you see their revenue growth is actually dropped a lot, 1.1%, but the operating margin is good. And again, the capital expenditure is quite low here. So return on investment is very high, 62.6%. TSMC is the market leader in the foundry, no question about that. And it's so much of dependency on TSMC. All these companies can make profit. Say Nvidia, Qualcomm, Broadcom can make profit only if TSMC is able to supply their chips. So Revenue growth is 4.12%. The operating margin is quite good, but capital expenditure you can see 43%. So that is much higher than Intel. And see if you the kind of chips they are actually making: smartphone 46%, high performance computing 37%, IoT 99%, and automotive 2%, and other 3%. Semiconductor equipment supplier, Applied Materials. So basically Applied Materials, I just wanted to show the Applied Materials, the products and how the financial is there. So semiconductor systems, they make 67% of the revenue comes from the semiconductor system, and then they do supply globally, service also, and then display and adjacent market of 10%. So their market capitalization 54%, revenue growth 12.3%, operating margin 22.9%, capital expenditures to sell is 3%. So this is the basically chart of how the different companies are for the Applied Materials. So you can see Applied Materials, it's equipment suppliers. So Applied Materials holds 20% of the market shares, ASML holding 20%, Lam Research 14%, Tokyo Electronics 14%, and the rest of the other players are below 10%, basically market capitalization. Yeah, this is the topic I had till now on the very high level of semiconductor trend, how the companies are doing, how they're making the revenues, what is the future product demand, things like that. So any questions so far, anyone? So Mr. Anil, so if you want me to go to the detail on the design flow, or it's okay to be for today?
Bijan, if you can touch this will be interesting to the students also, because some of the
Yeah,
students are from PG and PhD,
sure.
so they will get some idea
Yeah,
from this.
I'll just give a high level how the flow works. For example, I have a memory circuit design team of say I have 20 experienced circuit designers actually for so basically how we are working on different um, how from spec to our product it goes. I'll tell you. So I'll give a brief summary so it will be helpful. For example, in our company we have different business units actually. So we have ASIC division, we have broadband division, we have uh, CSG, we have PLP. So based on their application, so switch supplier, so different applications. So at different technologies, they architect a chip. So when they architect a chip, they give us, say, this is a big chip actually that will have multiple GBs of memory content. Okay, gigabytes of memory content. So and then they will give us just configurations, so words and bits, and they will say we want to make this chip this much millimeter by this much millimeter, and they wanted to have a area and power spec, and then they will have a frequency target. So with that, we say, for example, they will give 500 instances of memory. Then what you do, you have memory optimizer actually. What it does, it will take those raw instance configuration. It means it will say the words and bits, and then based on words and bits, I'll get a frequency target and what voltage it will be operated for. So I have a database in our from our previous technology. We'll scale the database where I can say this much for this much frequency target. If I go across, I have so many memories. I have single port SRAM, I have dual port SRAM, I have uh, synchronous RF, I have RF, I have all different kinds of dual port, pseudo dual port I have. So I have all this database in our MEM portal. So it will give the request and it will ask this is the frequency. The MEM optimizer, what it does for the chip frequency requirement, it goes and check this configuration, what will be the best area, power and performance with this frequency. So it will give us a list of instances. And then with that list of instances, we do a selection. When what it does, sometimes in the chip level, right, it gives a very big instance size, but based on the maximum configuration supported by a compiler, it will also break the instance and it will tile multiple times, and then based on the tiles it will also calculate the area overhead because of tiles and also the power overhead because of tiles, and then ultimately it will give a mem optimizer, give us a uh, exact memories which are going to be used for this chip. So I have 5 categories of compilers and I'll have say 50-50 instances for each compilers. So and then in my team I'll distribute, I have different team. I have SRAM, single port SRAM, high speed, single port high speed SRAM team. I have high density team. I have synchronous RF team and I have asynchronous RF team. I'll go to my team, I'll tell these are the instances we have to give for this chip. And then each and then looking at the target, actually they'll, so that's one product, right? I'll get multiple product requests for different chips. So then based on those product in a particular technology, they'll define the range for each and every compiler. And then when they'll go to the development phase, they'll basically do the statistical yield projection. We target PPA. What it means, say for example, if my memory is used 5 MBs in the chips versus I have another chip where my memory is going to be used 512 megabit, and I have another chip, my same memory is going to be used 1 gig. Now because of this usage, my spec is also getting tighter because of the statistical nature of the devices. So now I'll go and target 1 gigahertz. If I go and target 1 gigabit of usage, then I have to cover a lot more sigmas in my design, in my statistical yield. So with that, my design will be very slow if I use 1 gigabit target design to a 1 megabit target design. So again, we'll split the design based on the usage. So that the designers we have statistical tools available, and based on that we classify based on the usage, and then we do the internal architecture, whether it's a low power requirement or the high performance requirement. We do the circuit design and, and layout techniques also. We do very thorough layout feasibilities because high performance layout is different, low power layout is completely different. If I have same memories, my layout is techniques totally different, my circuit design technique is totally different between these two. Then and then basically assume in low power I got one low power block, and that will be in, now that I'll get the LVS clean database for that, and then we'll do the extractions, and then you will do the characterization. Now in the characterization, what new things came is that LVF, it's called Liberty Variation Format. So different, basically we have to consider the variation also, that variation of the each and every device, basically I have to account, and basically I have to make sure I'll give a Liberty model which will have 2 sigma, 3 sigma, 4 sigma, 5 sigma variation. Based on that, my liberty, yeah, I can have a different liberty model, so based on the chip requirement. And then once I have those optimized layout and design, then we run the race conditions, and RC plus device sensitivity. So these every block I have present here, right? It requires hours of explanation, go into more details on that. And then basically, because it's completely based on the experience and the design technique you use, the tool you use, the skill set we have. So everything is a domain. Then we'll go to the EMIR and Power XT. It's not just theoretical EMIR and Power XT. We do face a lot of hurdles in Power XT. Now in earlier days, right, don't we generally in the Liberty model we didn't consider the power extraction because it's a huge simulation over it. Now we have a software capability to extract only the M0 and just below VR0. So that is most of the timing is getting impacted by the lower level below VR0. So that facility we have now. So with that, if we give our design, we give our design to the chip team, so they'll see much more accurate number in timing and power because we have. So this is the complete design flow, Anil, as I said. So if every block is a topic to discuss for 2 hours. So I don't want to go detail more on that one. So then I have a lot more technical things to cover, but I think today this will be good enough, I guess, right, Anil?
Right, right. So, should I ask for the questions now from
Yeah,
the
sure,
audience?
sure.
Yes, please. Any questions from your side? Yes, anybody? Bijan, which is the fabrication unit that you send to your chips?
So far it's TSMC, but
Okay,
they're facing a lot of crunch because of the high demand. So far it's TSMC. I don't think any other foundry can support so much of mass production. Actually, they don't have so much of production. Still, the Samsung to catch up to the TSMC, they're far behind. So production we required, so many chips we required, we can't go anywhere other than TSMC.
okay. And what is the biggest memory size that you are providing now to your customers?
So we have different categories. Say for example, we have 2K cross 320 is the biggest SRAMs we support, because after beyond that, that instance is no more useful because it will be really slow in the access time and all. Instead, we think it should split it. If chip requirement is higher, we just split it. We build multiple instances and do tiling at the chip level.
Okay, right. And can you please just give a brief that what kind of skill set that is required to the students to focus on more from your side? You take a lot of interviews.
Hmm. So majorly there are different skill set. I'll tell you. So one is design. Actually, design generally what my experience is that it's very difficult to make a designer. Actually, it comes from their inherent what is called some skill set they get it. Actually, I mean, I found based on my 18 19 years of experience. So you can be a designer, you can be over a period of time, you can be a designer, but a great designer actually they get different mindset. I found very few in the industry. And then you have automation skill set that is also required. Without that, then you have to be moderate in design, moderate in good in automation. That is another skill set we use for characterization. And then basically, so pure circuit design, then design plus characterization, and then you need for verification. So verification is again you need design knowledge, but you will not exactly do the design, but you need to do validate all the functionality. You'll do the power of checks, you'll do the model checks, things like that. So those are areas also we are recruiting a lot. And then basically experience guys, and then layout side, and then layout also again, that layout, start with the layout and convert yourself from the design to the design side will also gives very good flavor, because many designers are very theoretical, they need to know the layout also, so that is another things people should not forget. And then cheap level and the SOC design, right? This is another. So mainly all the timing closer, SOC level, setup fold, checks, clock synthesis. Those are the areas, and it's a huge area actually, if you see, right? So lot of openings in the SOCs. In the design, memory design side, we don't have lot of opening as much as SOC designers has, but the circuit design experience actually is cumulatively add on with the over period of time. You will, because you'll not be too much dependent on the tool. Your intrinsic skill set is valued over time.
Okay. Yes, to the audience, to the students, any question from your side? You have any doubts, so please ask your question to raise your hands, and I will put your point to the Bijan, to Bijan. Am I audible?
Yeah, you're audible, Anil. I don't know. So it's a Saturday. People not. I think I'm giving a talk in wrong time. People should enjoy this time, right?
We took your time out of your busy schedule, so we are thankful to you given that.
No, I thankful to you all actually. Listen to me, and it's a fun to talk, because generally we just so much industry centric, right? We don't contribute to the society so much. Actually, I'm telling you. So this contributing part of it also feels. I feel good about it.
Thanks, Bijan. Thanks for that. So I know you for the long time that when we were in Noida,
Yeah, yeah,
so we spent a lot of time with our teams, spending the nights on here.
yeah.
So should I wind up now? Any questions? Anybody? Yes, Ranveer,
Yeah,
please
I have
raise
a
your point.
question.
Yes, Ranveer. Yes, please go ahead.
Yeah, go ahead, please.
Yes, sir. Like in EMR IR drop, where we
Yeah.
check that EMR drop. Like which tool we can use, or after complete layout design, can we do that?
Yeah, so there are different levels basically. So we do use synopsis tools. Basically, that's called XARA. I think most of the people are use that tool now. So we have uh, a block level EMIR also we run while laying out one particular cell. We do run EMIR, and then most importantly at the instance level, when you have the full instance LVS clean, and then basically you have to make sure that, say for example, memory goes till metal 5, right? Metal 4 to metal 5 in lower technologies, 5 nanometer, 7 nanometer. So but in the actual reality you'll have so above metal 5 we assume that is a ideal source, but in reality nothing is ideal at ml6, uh, metal layer 6. So say every 5 micron we drop vias metal 5, metal 6 vias in the instances. VDD 5 micron, VSS 5 microns, and then we run EMI at that stage when I have the instance and all the internal powers are connected properly. Then we run the EMI through XARA tool, and wherever it flags, right? For example, uh, IR and EM again both two separate things. IR actually it slows down the memory, and EM it functionally breaks the basic metal connections, right? So we have to have IR improvement. While doing IR improvement, we have to make sure we have enough metals to feed the current there. Okay, that particular where we see the airdrop, that particular metal layer, and then we have the enough connections actually from and then for the EM actually if some metals are very thin actually you'll see the EM violations, so you have to increase you have to add parallel tracks to basically clean up EM, so that instance level you'll be doing that.
Sir, can we estimate EM or IR drop using during post layout simulations, or we have to do separate analysis for EM or IR drop?
No, PA post layout simulation, that's what I said, right? Power XT, you can do that, but we have to do both. One is EMIR, that you have to clean it first. Okay. Now, even if you don't see any flag in IR simulation, IR drop analysis, right? Now, if you do actual full extraction and simulate it, right? Actual functional simulation or timing simulation you do, you may still see IR drop, because when you do the that particular IR drop, right? So it depends on which timing is getting impacted, right? When you only run the EMIR separately, it will see the maximum drops. It will flag. Say if you see 70 millivolt drop in M0, you'll say 70 millivolt drop, right? And now how 70 millivolt drop is going to translate to your timing impact, that will come up from your timing simulation with the air drop. So both you have to do. And you have to fix
Okay.
both.
Okay, sir.
Good question. Thank you.
Thank you, sir.
Hello.
Yes, Pius.
I had a question. Are most of the job opportunities in this sector mostly in manufacturing and testing?
Can you just repeat again?
Ranveer, can you please repeat?
Yeah. Are most of the job opportunities in this sector mostly in manufacturing and testing?
So you are saying that you have opportunities, huh?
No, no, I wanted to ask, are most of the opportunities in this area mostly in manufacturing and testing only?
No, this is not manufacturing and testing, right? This is, we don't have any manufacturing in it in India, right? So it is in Taiwan. So testing will be there, but mostly in our design. So it's a design testing. It's not that the simulator design testing. It's like validation. So job
So,
opportunities for manufacturing is not there in India.
no, even if I go abroad, are most of the job opportunities in the manufacturing area, like factory-based industries, or designing opportunities are coming up?
I think design is coming up, right? Manufacturing is, you have to go either to Taiwan or China, but I don't have much idea of how how they are scaling up, what the exact skill set they look for. But we are, I think, more opportunities will be in the design areas actually, because that's where all the fabless players are playing, right? Fabless players need R&D on the design side. So I think, and you'll have good appreciation on the skill set with the fabless rather than manufacturing. You will be stuck to a particular fab, and it's like a manual work. I mean, not manual work. It's a particular skill set. You will not may not be able to scale up your skill set on the fab.
Oh, okay, thank you.
Yeah. So if you are in the design or in this fabless portion, right, it's easy for you to switch to any domain actually, easily
That's
based
right.
on the, yeah.
Yes, any Pius, do you have any question?
Sir, one last question. Actually, when we design analog design, when we go for analog design, same analysis for IR drop or that EM drop.
Yeah,
Like
that
like when we are doing digital analysis design, we are doing that timing analysis. For analog design, we have to do that timing or STA.
it's not, it will be STA will be the block level, but for analog, definitely you have to, the fundamentally you have to check the EM, right?
Okay.
Okay, whether that EM is actually satisfied or not, and then also the current requirement for that particular airdrop specially also required, because you need to have analog block to be properly supplied with the feed with the currents, right? So definitely airdrop will also be there. So, but I don't have experience on analog much, so I can't comment too much on that. But definitely I think it's a part of the chip, right? That blocks also sit in the part of the in the somewhere in the chip, and we need a block level STA cleanup also, right, for that chip.
Okay, sir. Thank you.
Yeah.
So any question further, or I should wind up here? Yes, please. So I think Bijan, no question from anybody now. So
Okay.
I'm personally thankful to you and from our student side and faculty side to spare your time and give us a talk on this topic.
Thank you. Thanks everyone. Thanks Anil, my friend.
Thank you,
Thanks.
Bijan, and
Thanks. You remember
take
me.
care. Take
Yeah.
care.
Take care. Chalo. Bye. Take
Bye
care.
bye.
Enjoy.